Welcome to Lesson 13C, Boundary Layer Momentum Thickness. In this lesson, we define momentum thickness and derive an equation for it. Then we'll discuss momentum thickness for the Blasius boundary layer and compare it to two other thicknesses and streamlines. I'll refer back to the control volume example problem that we solved in Lesson 4A, namely flow over a flat plate, where we used the control volume technique. Recall our control volume had the wall as its lower boundary and a streamline as its upper boundary, the inlet at the beginning of the plate and the outlet at some x where there's a boundary layer that has developed. The result of this control volume analysis was that d over b, which is the drag per unit depth into the page from the leading edge where x is 0 to this downstream location x, is equal to rho u squared, integral from 0 to infinity of u over capital U, 1 minus u over capital U dy, where capital U is the free stream flow far upstream. Let's take this integral and we'll define this as theta, which is the momentum thickness. What does theta mean physically? Well, we see from this equation that rho u squared theta is the loss of x momentum flow per unit depth into the page due to the presence of the boundary layer, where we know from control volume momentum analysis that the drag on the plate comes about as a direct result of momentum loss or momentum deficit in the boundary layer. It's somewhat similar to delta star except for momentum instead of mass, where delta star is a result of mass deficit in the boundary layer. Even though we derive this equation for momentum thickness for a flat plate boundary layer, it holds for any boundary layer. So in general, through any boundary layer, theta is the integral from 0 to infinity of u over u times 1 minus u over u dy. This is our equation for momentum thickness. Now let's calculate this momentum thickness for our Blasius boundary layer. Recall our similarity variable eta, so we can write dy as d eta square root of nu x over u. So theta becomes square root of nu x over u, integral from 0 to infinity, now in terms of eta rather than y, and knowing that f prime is u over capital U for our Blasius similarity solution, this becomes f prime times 1 minus f prime d eta. Well, we can integrate this integral by parts. We've done this before, where the general form is integral of w dz equal wz minus integral of z dw. Here we let w equal 1 minus f prime, this term, so that dw is minus f double prime d eta, and we let dz be the remaining part, f prime d eta, which we can integrate to get simply f. Thus our equation becomes theta equal square root of nu x over u times wz, which is 1 minus f prime times f, and we put in the limits of integration, 0 to infinity, plus integral of z dw, where z is f, and dw is minus f double prime d eta, where these two negative signs have canceled, and I need a big bracket over this whole thing. Well, let's look at these limits. We know that as eta goes to infinity, f prime of infinity goes to 1, so this term becomes 0 at the upper limit. At eta equals 0, f of 0 is 0, and thus this term goes to 0 at the lower limit as well. So this whole term goes away, and we're left with theta is square root of nu x over u, integral from 0 to infinity of f double prime d eta. Now I'll ask the question, how do we integrate this? Can we integrate by parts again? No, that wouldn't help here, Sean. Perhaps we can go back to the original ODE and substitute. Brilliant idea, Albert. You must be a genius. Well, we'll let history determine that. Okay, well, let's try this. This is kind of a trick. If you recall our Blasius similarity equation, it was f triple prime plus 1/2 f double prime equals 0 for the case where we took constant c equal 1/2, which is the case we solved for in MATLAB in a previous lesson. Well, as Albert noticed, this term is the same as this term, so we can solve for f double prime equal to minus 2 f triple prime, and plugging this into here gives us theta equal minus 2 square root of nu x over u, integral from 0 to infinity of f triple prime d eta equal minus 2 square root of nu x over u, f double prime, since this is now a nice simple integral, and evaluated over the limits.
I love this trick.
Yeah, Albert, I love this trick too. Now let's examine f double prime at these limits. As eta goes to infinity, f prime of infinity goes to 1. In other words, u over u goes to 1 above the boundary layer. And if we take the derivative, f double prime becomes 0 when eta goes to infinity. So when plugging in the upper limit value, this term goes away. Note also that this negative sign and the one we get by subtracting the value at the lower limit cancel. Thus theta equal 2 square root of nu x over u, f double prime of 0. And this is valid for the Blasius boundary layer. Well, now all that's left is to find this value. F double prime of 0 comes from our Runge-Kutta solution, which I solved in MATLAB, and we've seen this before. The columns are eta, f double prime, f prime, and f. And if you recall, we had to guess the value of f double prime at eta equals 0, and we kept guessing until f prime goes to 1 at what we're calling infinity, and our value was 0.33205. So f double prime at 0 is 0.33205, which I write here as well. Finally then, theta is 2 square root of nu x over u times 0.33205. We're dividing by x to make this non-dimensional, and rounding to 3 digits, theta over x is 0.664 square root of nu over ux, and we recognize this as 1 over the Reynolds number. Thus, theta over x is 0.664 over the square root of rex. This is the momentum thickness for the Blasius flat plate boundary layer. I'll make a quick comment here. It should not be surprising that theta is proportional to f double prime at 0, since f double prime at 0 is proportional to the shear stress tau w at the wall, and theta itself is related to the drag on the plate. So this f double prime at 0, or at the wall, turned out to be critical not only for solving the differential equation, but for calculating theta. I also comment that this equation for theta is the same form as that for delta over x and delta star over x, but with a different constant. Finally, I grabbed this figure from my undergraduate fluids book, where I had plotted delta and some streamlines, and now I carefully plotted also delta star in green and theta in purple. For delta over x, the constant is 4.91. For delta star over x, the constant is 1.72, and for theta, the constant is 0.664. So theta is about 40% of delta star, which is itself about a third of delta. Finally, I comment that neither theta, nor delta star, nor delta are streamlines. In fact, these streamlines will eventually intersect and pass through all three of these thicknesses if you go far enough downstream.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.